In the last video, we talked about the extreme value theorem, and now we want to go ahead and see how we can use this extreme value theorem to help find mins and maxes of different functions on closed intervals. So let's see what we have here. We're going to take the ideas that the extreme value theorem gave us and kind of help formulate them into kind of an awesome method to help answer questions like example 7, which are going to ask us to find the absolute extrema, that is the absolute extremes, the absolute max and the absolute min of a function on an interval. So here's the first thing that we should note. If I want to find absolute mins and maximums of a continuous function on a to b, then this method is going to work. But I have to make sure I'm on a closed interval and working with a continuous function. Now the first thing I would do is I would find all of my critical points, since those are going to be important spots where there may be a min or a max. So I'll get all my critical points, and you can start to imagine I'm going to create them in like a list. So I'm going to put down some critical points. So maybe I find like 2 of them, okay? Imagine here I'm making a list, I have critical points. Then I'm going to plug in my values of A and B as other potential candidates where there could be high or low points. To see that, just take a look back at some of the examples that we drew in the previous video. You can see here that if I had actual points as opposed to holes, the endpoints of my interval could correspond to highest or largest points, kind of like what we had in this picture. So they're important to actually consider when filling in this little table. Now, the other thing that I can do what I do once I have all of these points is this is my list of potential candidates for highest and lowest y's on this interval. Well, then I can just try to go ahead and go to my function and calculate their associated y values. And I can see which one of these spits out the biggest value and which one of these spits out the smallest value. So that's kind of combining steps 2 and 3. Find the y values and kind of fill out my table. And then the largest of these is my absolute max, and the smallest of these is my absolute min. So let's go ahead and see how we're going to actually use this method here on example number 7. Again, remember, we're going to have to first check that our function is continuous and that we're working on a closed interval from some value to another value. So let's see here on example number 7. I want to find the absolute extreme of this polynomial function on the interval from 1 to 5. Okay, so the closed interval part, boom, that's already checked off. But we should check to see that our function is continuous. Now I'm going to go ahead and state here that clearly f of x is continuous on the interval from 1 to 5 because it is a polynomial function. And remember that polynomial functions are going to be continuous everywhere. So now I know there has to be a min or a max actually here on this graph by the extreme value theorem. Right? On this interval, at least, there's an absolute min and an absolute max. So let's go ahead and try to find it. First thing I have to do is identify my critical points. Remember, I'm going to build a list of my potential candidates. So let's see. Let's start by just saying that we calculate f prime of x is equal to 6x squared minus 30x plus 36. Okay. Ooh, now I'm actually going to go ahead here and just quickly note that if I factored out a value of 6 here, this would look like 6x squared minus 5x plus 6. And this could actually be factored even further into x, let's see, 6 times x, what would that be? Maybe minus 3 and x minus 2. That could work out beautifully. So now I can go ahead and check to see when my derivative is equal to 0 and when it's undefined. So I'll say f prime of x is equal to 0 when, well, this is pretty easy, whenever this is equal to 0. So this would be when x is equal to 3 or when x is equal to 2. I can also see that f prime of x is never undefined, right? There's nothing I can plug in that's going to cause this to be divided by 0 or square root of a negative, natural log of a negative, things like that. Nothing going to happen like that. So it seems like I found all my critical values. My critical values are right here, 2 and 3. I'll go ahead and mark these. These again are my critical values. So what I'm going to do is make my list of potential candidates. Okay, so let's see. My potential candidates for where there might be high and low points on this picture are going to be at 3, at 2, at 1, and at 5. Notice I'm only working on the interval 1 to 5, so if any of these values had been outside of this interval, I would have disregarded them. So let's see what we have here. I'm going to go ahead and create my table of values. This is at least one way that I like to set this up. So here are my x's, 1, 2, 3, and 5. These again are my potential x's. And I'm going to go ahead and now compute what f of x would produce if I was to go ahead and actually crunch these out. So let's see, what would happen if I plug in the value of 1? Well, this one's here pretty easy. Let's see, 2 minus 15, and then plus a 36. I think you could double check here. I end up with the value of 23. If I plugged in a 2, things get a little bit more complicated. Now for the moment, I'll just go ahead and give you what these values actually end up as. You could double check them on your own. This part of the process, of course, is rather simple. But now that I know that these are, again, all the potential spots, these are my potential candidates for where mins and maxes occur. Now I can see what values they generate. And it's pretty easy to spot that 55 here is the biggest y value out of all of the potential spots where there could have even been maximums on the graph. So I can state here that f of x has an absolute max of 55. And I know it occurs when x is equal to 5. So it occurs at my endpoint. I can also see that f of x has an absolute min of 23. Remember, absolute maxes and mins are y values, but it's got an absolute min of 23, and I can see that that occurs when x is equal to 1. So here, my mins and my maxes, and my absolute min and my absolute max occurred actually at the endpoints of my interval, which just goes to show you how important it is to not forget to check those endpoints, because sometimes the mins and absolute maxes might occur there. So this is the concept of the closed interval method, and hopefully this gives you an idea of how we can find mins and maxes for a function like this. Now, a great way to go ahead and just quickly double check to see if you did your work like this correctly would be go to your calculator or go to Desmos online or something like that and actually type in this function and look at the interval from 1 to 5, and you should be able to see that 55 is the highest y value reached on this interval and that 23 is the smallest y value reached on that entire interval.